Hi everyone, this is Kumar this side and welcome back to Chemistry Universe. In this video, we'll be starting phenols and this is part 1, and in this we'll talk about the introduction and preparation of phenols. And as I have said many times in my video, you must watch this video like you would attend a class. So make sure that you have a notebook and you are going to write down everything that we are going to talk about in the notebook, irrespective of the fact that in our website chemistryuniverse.com you will find the PDF of the entire presentation. But it is important to note down, because to focus on what is being taught, you need to write down stuff. And there would be examples in which you will have to work out the product, and there you need to pause as many times as you want in between while writing, and make sure that you attend this with as much of a seriousness as a class. Now, this being a relatively short video, I would prefer that you watch it in one go. So don't watch it in installment, watch it at a time when you think you are quite focused to study, and make sure that it is at that time when you sit down and watch this video. With that out of the way, let's get the ball rolling and let's start with part 1 of phenol, which is introduction and preparation of phenols. All right, so here we go. So we'll start with the introduction first. Let's understand what are phenols, because phenols and alcohols seem very similar. Both have OH groups. So the compounds having hydroxyl groups directly attached to a benzene ring are called phenols. So this means that if you have a benzene ring and you have a OH directly attached to it, it's not an alcohol, it's a phenol. And functionally, alcohols and phenols are different, which is why we are keeping it as a separate functional group. Their tests are different, their behavior is different, just because of the fact that it is attached to an aromatic ring. Now, of course, phenol by itself is only when a OH is attached to a benzene ring or a substituted benzene ring. But when you have other aromatic ring, there are families of phenols. They are not called phenols, but they are similar in their behavior to phenols. Okay, for example, this one, we call it phenol. We can call it benzenol, we can call it carbolic acid, we can call it hydroxybenzene, even though technically speaking, you can call it as phenol or maybe even benzenol as far as the IUPAC name is concerned. Now, of course, now what happens is we will also talk about some other typical types of compounds, which are of course phenols, but they also have some common names which are pretty important. Say, for example, this one. If you have a CH3 at the ortho position, we call it orthocresol. Of course, you can also call it orthomethylphenol. And in IUPAC, it will become 2-methylphenol. But one of the common names of this is cresol, orthocresol. So you need to understand this. You need to remember all these names. And obviously, when it is attached in the meta position, you call it metacresol. Attached to the para position, you call it paracresol. Now, what happens when you have two OH groups attached to the benzene ring? And if they're attached ortho, the common name is catechol. If they're attached in the meta, it's called resorcinol. And if it is para, it's called quinol. Now, as I said, you can even have other type of aromatic rings having this OH. So if you have the OH attached in the naphthalene, it's called, now, since this position is always numbered 1, this position is always numbered 1, and this position is always numbered 2. So you can call it alpha, you can call it beta in case you want to use the common name. So this is called the alpha naphthol. And if it is attached on the position number 2, we call it beta naphthol. So now another very common phenol that you will find is this one, that is 2,4,6 trinitrophenol, and this is commonly called picric acid. In fact, it is so much acidic that it behaves almost like a carboxylic acid. And then, of course, when you have anthracene, remember in the numbering, these two positions get 9 and 10. 9 and 10. So remember, it doesn't matter whether the OH is on 9 or in this position, it will be still named 9, because we will make sure that the OH gets the lowest number as possible. But the numbering pattern has to remain the same, which we have discussed before. And this is called 9-anthrol. And we can even have phenanthrene, And in phenanthrene, this position it becomes 9-phenanthrol. And if you look at this one, well, this is pyrogalol. In fact, if you remember, this is used in gaseous state, especially in eudiometry where we want to absorb oxygen. Pyrogalol has the ability to absorb oxygen. All right. So aromatic alcohols are those in which the OH group and aromatic ring are present together but not joined directly. So what this basically means is, if you are asked what is an aromatic alcohol, phenol is not an aromatic alcohol. Phenol is a separate functional group. So an aromatic alcohol is something in which there is an aromatic ring and there is an OH, but they're not directly attached. They are attached through, let's say, an aliphatic type carbon. This is benzyl alcohol, and this is 2-phenyl ethanol or 2-phenyl ethane-1-ol. So that is about the basic introduction. Let's look at the preparation. Now in the preparation, first we start with from benzene sulfonic acid. Now what happens is, now I'm going to make a statement here. Just look at the statement. I'll explain the statement once it is made. The fusion of aromatic sulfonates with caustic alkali at high temperatures gives phenol by displacement of sulfite ion. Now try and understand this statement. This is what it means. It says the fusion means heating. Fine. Fusion of aromatic sulfonates. Now what is aromatic sulfonate? Do you remember benzene sulfonic acid? There's a benzene ring on which you have an SO3H attached. So if I reacted with, let's say, NaOH or any alkali, I'll get the sodium or potassium salt of that. So that is the sulfonate. So you heat the aryl sulfonate, that means SO3Na attached to benzene, that is aryl sulfonate. You heat it with alkali, NaOH or KOH. Now that OH minus will nucleophilically substitute on that carbon where the sulfite ion is present, and that OH would come and sit there and the sulfite ion will go. And the mechanism that is followed here is the benzene mechanism. If you remember nucleophilic substitution of aryl halides, we discussed about the fact that benzene mechanism is followed whenever we have unactivated ring for nucleophilic substitution. So this is the fusion of aryl sulfonates with alkali. All right. So let's look at the reaction. You have benzene sulfonic acid treated with NaOH and it will form the salt. And further you can add NaOH, or you can have NaOH excess in the beginning, and then you heat it and you will get nucleophilic substitution, and it is going to give you phenol and it will give you sulfite ion. SO3 minus will go as SO3 2 minus. And the mechanism, if you remember, is benzene. Now you can also get phenol from benzene diazonium chloride. If you remember, we did this in aryl halides and I gave you a lot of reactions of this particular compound, that is benzene diazonium chloride. All of them are ArSN1. So when benzene diazonium chloride is warmed with water or steam is passed, phenol is obtained with evolution of nitrogen. So you have this one and you have steam being passed, heated strongly, you get phenol. And the mechanism is ArSN1. Now the next one is a little sort of a dumb kind of a preparation, but anyway, you are talking about preparation of phenol, so it doesn't matter where you get it from. You can get phenol from salicylic acid. Now it's a different fact that salicylic acid itself is produced from phenol. So one might say, why the hell do we need this salicylic acid to produce phenol? But anyway, that's a preparation that you do have. So phenolic carboxylic acids, ortho, meta or para, on heating with soda lime undergo decarboxylation to give sodium phenoxide, which on acidification gives phenol. If you remember, we have done this. We have done decarboxylation. If you remember, in the preparation of alkanes, we did decarboxylation, and the same thing happens here. You can do a decarboxylation, and salicylic acid is basically the COH present on a phenol compound at the ortho position. But of course, the COH can also be in meta and para. Of course, you don't call them as salicylic acid, but they can also be decarboxylated. The COH can go as CO2 and you will get phenol. So you have salicylic acid, soda lime, decarboxylation, and you get, of course, you will get the salt, because you are talking about a basics medium. And in a basic medium, what always happens is you do get the salt of phenol, because phenol is soluble in NaOH. And now you have to acidify it and you'll get phenol. Now you can also get it from Grignard's reagent. We have done this. We have done Grignard's reagent in organometallic compounds. So what we do is we take an aromatic Grignard's reagent, we react with oxygen molecule. Now this is the way you can understand it. I'm not saying this is the mechanism, but this is the way you can understand what is happening. So make oxygen like O double bond O. And what you do is assume there is a homolytic cleavage here. So you have a radical here and you have a radical here. And break this pi bond to create a diradical homolytically. Now one of the O dots attaches with the Mg, the other O dot attaches with the aromatic carbon. So what happens first is you get something like this. Remember, this is only to make you understand or help you make the product. Now I'm going to react this with another molecule of Grignard's reagent. And this is what we are going to do. What we're going to do is, remember we have pH MgCl. Okay. So what I'm going to do is that this pH MgCl breaks homolytically. So I get a pH dot and an Mg dot. And this breaks homolytically. You get two O dots. Okay. So now what happens is this O dot picks up this MgCl dot. So you get PHO MgCl. And this pH dot combines with O dot to get another PHO MgCl. So basically what happens is you get this. I mean, if you can remember without this logic, it's okay. But if you want a logic, this is the way the logic goes. I have pH MgCl. Remember, I break this homolytically. This is only to make it. It's not the mechanism. And then this breaks homolytically. This O dot combines with this MgCl dot. And this O dot MgCl combines with the pH dot that you'll get. And you get two molecules of PHO MgCl. Now it's just a matter of acidification, because this is a salt of phenol. And you will find acidifying this would give you this phenol. The next preparation is called the Dove's process. This again is simple benzene mechanism. You have chlorobenzene. We have done this in aryl halides. And you heat it with NaOH at very high temperature and pressure. And that is, of course, when the Cl is not activated, when there are no withdrawing groups, it will undergo benzene mechanism and the condition will be vigorous. So OH will replace the Cl, but remember it's a basic medium, so you get ONA, and then you acidify it and you get phenol. And as I said, the mechanism is through benzene. Now you have picric acid. Now you can, of course, if you want to make picric acid, one of the ways of doing that would be, you have 3 NO2s already. That will make the ring highly activated towards nucleophilic substitution, which we saw in aryl halides. And this will undergo by ARSN2. So you have NaOH and you can do it just at room temperature. You have ONA and acidify it, you get picric acid. Now another method for preparation is the Rachig process, which we have again discussed before. So you reacted with HCl in the presence of O2 and the catalyst uses CuCl2 with FeCl3 and takes about 300 degrees Celsius, and you will get chlorobenzene here. You don't have to worry about how it is formed. Just remember this is the way it is formed. You get chlorobenzene here. And this chlorobenzene, when reacted with steam at very high temperatures, benzene mechanism again, you get phenoxide. And of course, you get, since it is steam, you will get phenol. If it were a base, you will get phenoxide. The next is a very important preparation. It's called the Cumene hydroperoxide preparation. So let's understand what is cumene first. So there is benzene here and you have propene. Treated with acid, electrophilic aromatic substitution. We have done this. And you know that this pi bond will break towards the corner carbon. You get a carbocation because this is more stable. And this will attach itself to benzene like an electrophile. So it is the basically alkylation of benzene. So this is called cumene. This is called cumene. Okay. Now, when we react this with oxygen molecule and keep the temperature as this much, and this, as I said, is cumene. Now, what happens is this breaks homolytically. And now this is the actual mechanism. This breaks homolytically, and you get a dot here and you get a dot here. The pi bond of O breaks homolytically. You get a dot here and you get a dot here. Now, this corner O dot will take this H dot. The C dot will take the O dot. Don't you think we'll get this? This is called cumene hydroperoxide. This is called cumene hydroperoxide. Okay. Now what happens is that this cumene hydroperoxide reacts with H plus. Now the H plus can go to any of the two oxygens, but we will show it from that oxygen where the further reaction takes place. So that happens on this terminal oxygen. And there is no particular reason for this. I've again explained this before, that it's not necessary to know which oxygen it will go to, as you just have to make the H plus go to that oxygen from where the reaction can happen. Obviously, the H plus will go to all oxygens possible, and it will also keep doing intramolecular proton exchange. Now here, the water leaves, and as the water leaves, the oxygen becomes plus. You know, this molecule leaves, and this will end up becoming plus, which the molecule would not like because O is an electronegative element. So this bond breaks, attaches to O. It's like a shift of the phenyl group, and you will get this water released. Now you know that carbon is plus and there is water in the system. It will act as a nucleophile on the carbon, and you are going to get this one. And now there will be intramolecular proton exchange. The H plus will move to the oxygen attached to the benzene ring. And then you find that this H plus gets released, forming acetone, and this gets broken, forming phenol. So you get acetone and phenol. So I want you to go through this reaction once again, look at all the steps carefully, because now I'm going to give you a couple of questions based on this. And this is how it happens. You have some examples now. So again, as always told to you, make sure that you write down the example, pause the video, solve it on your own, and at the end, you play the video back so that you can get the solution and check whether you've done it correctly or not. So imagine that I've got benzene reacting with this molecule. And the same steps of cumene hydroperoxide. Remember, the first one was attaching H plus so that it can attach to benzene ring. And then we have reaction with oxygen. Then we have reaction with H plus and water, that is H3O plus. So I want you to pause the video now and make the product. And here is the answer. Now, the benzene obviously is going to become phenol. That's the end story anyway. But here, the what do you call, the ketone formed, remember, when we used propene, we got acetone. So basically, wherever there is a double bond, one of the carbons becomes double bond O. And you will find that you get this as the ketone. Try this example. And let's use the same set of reagents. Pause the video. Again, you'll end up getting phenol. But you got to figure out which particular ketone you're going to get. Remember, there are 3 carbons here. And you're going to get something like this. Because remember, which carbon gets attached. Now you need to understand which carbon gets attached to benzene. Obviously, the one that can form the carbocation better. This carbocation is better than carbocation here. And wherever you get the carbocation, that is the carbon that will form the C double bond O. That is what you need to infer from the mechanism. Let's try one more. So I've got nitrobenzene and I got this. Now, in this particular reaction, there is, of course, a bit of a problem, which I'll tell you later. First, let's check. Now, you will obviously get phenol. Of course, you're wondering, where do I get the phenol from? I'll explain. And then you get this as the ketone. Now, I want you to understand how this happened. Now, what must have happened is, obviously, this carbocation is more stable. So, this carbon gets the H plus, and this carbocation attaches to the nitrobenzene. Where will it attach? It will attach meta, because nitro is meta directing. So you have a CH here, you have a pH here, and you have a ET here. Okay. So now remember, it is this carbon that is getting attached. Okay. So now what happens is that, remember, you have this pH as well as this pH. Of course, it's a nitro pH. Now, if you remember the mechanism, you got cumene hydroperoxide, and this attaches to H plus, it forms water and leaves. This O becomes plus, and you need one of the two groups, this one or this one, to go and attach to the O plus. Now, the one which goes is the one which is electron rich. Remember, whenever there's a migration always happens for that group which is electron rich. So instead of this going, this would go, because this is withdrawing group. It will decrease the electron density of benzene ring. This will increase the electron density, and this would move. And the one that moves to O is the one that eventually becomes the phenol. So the rest of the stuff will become the ketone. So that is how you need to judge. So what do you think will happen here? Pause the video. Yeah, by the way, now coming back to the original question, I told you there is some kind of an issue here. And the issue is, even though we are trying to make the product with this, and whenever these two are given to you, you have to make these products, of course. But the problem is, this reaction is going to be very difficult to happen, because whenever the ring is strongly deactivated, you will not get alkylation or acylation happening. But perhaps what is happening is that, all these reagents being added one after the other, maybe the rate of the reaction may be pretty slow for nitrobenzene to form to get alkylated, but eventually this product can get formed. Of course, there is no particular data available that tells you whether this actually is formed or not. But I mean, if it is asked in an exam, obviously you'll go for it. Now remember, you just realize that again, it is this carbon that will attach to the benzene ring. This is ortho para directing. Majority will be para, so it will attach here. But as you can see, this is the electron releasing group. So this is the one that will move. This is the one that will shift. So it is this benzene ring that will shift, and you will eventually get this and this one. You can check it out yourself. Try this. Now remember, okay, I just want you to pause the video and make it on your own first. And here is the answer. Now remember, now this carbon obviously will attach to the para of this. Now you will wonder, you will think that, okay, I've got one benzene with methyl, I've got one more benzene with methyl. One is ortho, one is para. Which one do I prefer to shift? Because the one that shifts to the oxygen, remember, is the one that will become the phenol. Remember, shifting also depends on steric hindrance. Besides electron density, it also depends on steric hindrance. More hindrance will make it shift less. So this is the one that will shift, the one in which it is attached para. So it is the para carbon that becomes the phenol, and this part becomes the ketone. And then lastly, you have partial oxidation of benzene. And this is pretty fairly simple, just have to remember it. You can do oxidation of benzene partially and you'll get phenol. But using, of course, V2O5 as the catalyst. But if you were to do complete oxidation with this, you're going to get malic anhydride. This is called malic anhydride. Right now, you don't have to worry about how this is happening. You just have to remember that, this is happening in fact, and this is complete oxidation, and that is partial oxidation. And with that, we come to the end of the preparation and introduction of phenols. Now, as I told you, this video is going to be short. But again, there are a couple of reactions here. So you have to learn all of them, focus by writing and going through it again and again. And if you have any questions or any queries, you can put them in the comment section below. And with that, this is Kalyan Kumar signing off. Have a great and wonderful day. Have an extremely productive day. And thank you for watching this.